Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, 3-volume series I wrote from 2019 to 2022. Anyway, I'm up to chapter 6, which is on group theory, and I'm going through the subsection on different types of permutation groups. Today I'm going to talk about symmetric groups, which are a very important type of permutation group. So anyway, let's begin. So what are symmetric groups, or what is a symmetric group? Well, yesterday I defined a permutation group. It's just a group which is a collection of permutations of a given finite set. And it has to be a group. It has to satisfy all 4 axioms of group theory. Usually you start with a few generators. You just see what permutations you get from those generators, and that's necessarily a group. But what about the collection of all permutations of a finite set? That turns out to be a group. And it's actually pretty easy to prove that it's a group. I mean, you just have to prove the 4 axioms of group theory. You have to prove closure is the first one. That's pretty easy because you take any 2 permutations of a group of order n, say, and you multiply them together, or you compose them, as they say, you get another permutation. Remember, a permutation is just a bijection. From your set to itself, you compose 2 bijections, you get another bijection. So it's necessarily another permutation. So it is closed. What about associativity? Well, yeah, it doesn't matter which order you group the compositions. This is true of functional composition in general. You know, if you have 3 functions, say f, g, and h, it doesn't matter whether you do g of h first and then compose that with f, or you do h first and then compose that with f of g. I think I went over that before. So it is associative because of the associativity of functional composition. What about identity? That's easy. Well, the permutation that does nothing. The permutation just leaves everything alone. That's the identity element, because you multiply that by any other permutation, you get that permutation. Pretty obvious. What about inverse? I think inverse is probably the trickiest one, but remember that every permutation we can write as a product of disjoint cycles. Well, we can just invert each cycle. You know, in other words, remember I said like you write a cycle as something like if your elements of a set are s sub 0, little s sub 0, little s sub 1, up to little s sub k minus 1. Well, you can write them backwards, s sub k minus 1, s sub k minus 2, so on, up to s sub 1, s sub 0. You're just cycling in the opposite order, and I think it's pretty easy to see that if you multiply those 2 cycles together, you get the identity, because one cycle just does the other one. And since your group element is just a product of disjoint cycles, you can do it with each one. So when you multiply them together, you get the identity. And they commute because the cycles are disjoint. And so that proves that it's a group. But now you might wonder, well, how many? What's the cardinality of it? We call it Sn, by the way. We call the group or the isomorphism class of symmetric groups acting on a set of cardinality n, where n is a positive integer. We call that S sub n. And you might wonder, how big is S sub n? Well, it turns out the size of S sub n grows really, really fast with n. It's what's known as n factorial, which is it's the product of all the numbers from 1 to n. Maybe you've seen that before. For instance, 1 factorial is 1, 2 factorial is 1 times 2 or 2, 3 factorial is 1 times 2 times 3. Sometimes people multiply in reverse, doesn't matter because multiplication is commutative. You get 6 for 3 factorial. I'll just show you the table. Here's a table of factorials up to 10 factorial. And you can see they grow very fast. So already the symmetric group acting on a set of cardinality 10 has over 3 million elements, specifically 3,628,800. That's 10 factorial. That's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So these things grow very, very fast. And how can we see that this is the order? Well, it's pretty simple. I mean, what you do is, just look at what. Remember that a permutation is just a rearrangement of the elements. So there's 10. If we're doing a set of order 10, there'd be 10 possibilities for what the number one can be get mapped to. If your set was a set of 1, 2, 3, 4 up to 10, then one can get mapped to 10 different things, any of the numbers 1 through 10. Two can now only get mapped to 9 different things because we can't map it to the same thing as what would one get mapped to. There's only 9 numbers left. So then there's 8 possibilities for the third number, 7 possibilities for the fourth number, so on, all the way up to the 10th number, for which there's only one remaining possibility. So I think you can see it's going to be 10 times 9 times 8 times 7 times so on, and that's 10 factorial. Or in general, if your set had cardinality n, there would be n factorial permutations. So there's n factorial elements of S sub n. People don't usually deal with symmetric groups as big as acting on a set of cardinality 10. You'll rarely see that. You see these factorials, by the way, these come up in other areas of math too. They're very useful in combinatorics, also in probability theory and statistics. So it is an important function, this factorial function. In case you haven't seen it before. And I think most calculators today, or at least scientific calculators, have a factorial button. But like I said, it's a very rapidly growing function. But anyway, just to see the elements. So for instance, 4 factorial is 24. That means that the permutation group of S sub 4, the group of permutations acting on a set of cardinality 4, has order 24. It has 24 elements. And so if we started with a set 1, 2, 3, 4, there's exactly 24 permutations of that set, that ordered set. And this table, I've split it into 3 parts here. This shows you how every element of S4 acts on the order 4 tuple 1, 2, 3, 4. And you can see you get all 24 permutations of that set. So anyway, and they say a picture's worth 1,000 words, so I thought I'd add a picture. This is the graphical representation of the group S4. For instance, so this, I think these connections here, if I'm not mistaken, show you transpositions. You remember, it turns out this is an interesting fact about symmetric groups and about permutations in general. You can turn any permutation on S sub on a set of cardinality n into any other permutation by multiplying by a finite number of transpositions. Every permutation, turns out, can be built from a finite set of transpositions. Another way to say that is that transpositions generate S sub n for every n. So your generators don't have to be any bigger than order 2. Just transpositions or elements that just flip 2 elements. So if you look at this graph, which I think is a really pretty graph, for instance, 4, 3, 2, 1, they're right on top. Notice that's connected to 4, 3, 1, 2. That just has 1 and 2 transposed. It also connected to 4, 2, 3, 1. That has 2 and 3 transposed. Finally, 3, 4, 2, 1. That has 3 and 4 transposed. I think you get the idea. So this is how you can get all 24 elements of S4 from every other element. This is what's known as a graph. I'm not going to graph theory here, but every group, another interesting fact is that every group has a graphical representation, and this is a graphical representation of the group S sub 4, the symmetric group on 4 elements. So anyway, that completes my video for today on symmetric groups. So thank you for watching. Long live math, and I'll see you guys next time. Bye.